Well, hello and welcome to episode number 44 of the Wonder of Stuff Vodcast, broadcast live on Google Hangouts on air every weekend. This is the place you'll find news, information and commentary on science, engineering and technology subjects from the past week and beyond, and anything else that interests us from inside our tiny little human brains. As ever, my name is John Gardner, and to help us out on the journey to knowledge, let me introduce one of my colleagues this week, Ross Davidson. Say hello, Ross.
I was going to say hello, chap. That'll do.
Yeah, Richard's gallivanting around Northumberland, so he can't be with us tonight. So it's probably going to be a shortened edition. Oh, what's that? Everybody cheering. Well, there you go. So never mind. We'll crack on. We've got a couple of good topics, and we might have some ranting and raving later on and about anything that we can think of. But first off, we'll start with Ross's topic. Now, something that we covered last week was the announcement, this big announcement that NASA were going to make about Mars. Well, subsequently, they made that announcement.
They did, yes, and unfortunately, it wasn't about aliens. You know, we always hope.
Boo.
And it was about water on Mars. So basically, they announced that they found evidence for liquid water on Mars. Now, the way they found this is actually from the reconnaissance orbiter. We showed some of those pictures. So those pictures, along with chemical sort of evidence, it's a strong suggestion that there's liquid water there. Now, you may think, okay, excellent, right, let's just prove that by sending the rover there. Now, unfortunately, as we showed last week, the rovers aren't very close. And also the places where they've seen this evidence of these flows, it would be difficult for the rovers to go up there. So you'd think, obviously finding water, finding, potential life signs, they'd be scrambling to send another mission directly to where they've found this evidence and actually prove once and for all whether it is water or not. Well, it's actually not that simple. They're not actually able to do that.
Why is that, Ross?
There's a thing called the 1967 Outer Space Treaty, which, as you can imagine, was signed in 1967. And this Outer Space Treaty was basically signed by lots of representatives across the world. So President Johnson from America, people from the United Kingdom, Russia, Australia, Japan, Canada, Finland, some other places, signed this treaty. And basically what part of this treaty says is that it forbids anyone from sending any mission, robot or human, close to any water sources in case they contaminate them with life from Earth.
Well, immediately I can see a huge problem. If we were ever going to colonize other planets, which was always the plan for many people, we're a bit stuffed if it's like, we've got water over there, we can't touch it.
Well, this is the trouble, yeah. And obviously, we've already sent robots to Mars. What happens if we find evidence around them? Do you have to just turn them off? But basically, yeah, anything that gets sent from Earth is going to be contaminated with sort of microorganisms and bacteria.
So we've already contaminated Mars by putting the rovers on there.
Effectively, yeah. And if you did want to send anything closer to where we've actually seen evidence of water, we'd have to completely sterilize them. Now, the only way to do that would be to blast whatever it is with massive amounts of heat or radiation or whatever, which would work, but obviously would destroy any electronics on there. So it's a bit impractical. So there's various things that have been talked about. One of the things which may work, but again, it's one of these sort of difficult things. If robots were sent there that then built robots on the surface of Mars, those robots that were built on the surface of Mars should hopefully be sterile and able to go to where the sources of water are. But again, you think, what happens if those original robots contaminate the ones they're building? So it's a bit of
going nowhere fast.
Exactly, yeah. So it's something that I wasn't actually aware of, that Outer Space Treaty, and I was reading into it. It's quite interesting that the treaty itself, signed in 1967. So as well as sort of saying, we don't want to contaminate anywhere, because obviously, if you're going to get evidence of life, you have to get rid of any potential cross-contamination. Otherwise, people will go, oh, but what if it was this? But the treaty mentions things like give you a couple of examples of what's in there. The exploration and use of outer space, including the moon and other celestial bodies, shall be carried out for the benefit and in the interests of all countries, irrespective of their degree of economic or scientific development, and shall be the province of all mankind. So it's things like that. And also there's the one about outer space is not subject to national appropriation or claims of sovereignty. So, even though the Americans went to the moon and planted an American flag, the moon's not theirs. And there's other ones about...
I guess they've done... It's because they've done things in Antarctica and the Arctic. They've got treaties for that as well.
Yeah, exactly, yeah. So there's also ones about sort of like, anyone who's part of this treaty will be open to give assistance in case of an accident or emergency or whatever. So if there's an emergency landing and it's in your territory, in your ocean, you've signed up to be responsible for going and helping with the emergency evacuation or whatever. And there's also one about not putting nuclear weapons into space. So everyone signed this to say they're not going to put weapons into space or on the moon or anything like that.
What happened with Star Wars then? I thought the Star Wars, the Strategic Defense Initiative was nuclear.
I don't think.
No, that was lasers, wasn't it?
Lasers, yeah. It's to blow up any nuclear weapons. That one, yeah.
But it was okay, yeah, okay. It's a thin line, a thin margin, because
exactly, yeah.
It's laser radiation is still yeah, anyway.
That's true. So basically, yeah, it is one of these sort of... They're going to have to change it if we are going to go and colonize Mars. Because,
absolutely. That was the whole point.
Any plans to sort of send humans there, the first thing they're going to do is want to have a source of water.
And if there's already one there...
Yeah.
That's your basic building block. You're already well advanced if you've got water.
Mm-hmm, mm-hmm. So it's going to be interesting to see what happens with that as to whether they're going to. I don't know whether the need to basically find a way to sterilize things in space, because obviously, like I say, the way to sterilize anything that's been on the Earth is going to destroy electronics. So I don't know if there's a way of just sort of like having some outer shell that would be sterilized that goes around everything or something like that. But yeah,
really peculiar. I mean, so as it stands, even though we've had this, this definitive announcement last week that there is water on Mars. They've proved it from all the time-lapse photography that they've done. We want to go and colonize Mars. Everybody's, NASA and ESA and all of the major space agencies have made that a goal. Mm-hmm. I think it's fair to say that's out there. That's all proven. But we can't really, as it stands at the moment. So all of the also all of the official, all of the new Mars rovers and the surveyors that are going in future. How does that?
So they'll have to avoid any of these areas that we've found evidence for water. So yeah, we've seen those areas. There's probably some more areas that we haven't taken imaging of. What happens if they decide to plonk something there and it's right next to water? Like you say, would we have to switch it off? Yeah, I don't know. They'd have to drive away quickly.
But then it's contaminated. Then it's pointless.
Exactly.
So.
It's too late. So it would be interesting to see whether that's something that gets an update or whether there's a bit of a delay. And like I say, you expect now the next mission to Mars would be heading straight for those areas, because while it's fairly definitive that there is liquid on Mars, until there's a direct sample, everything's indirect. So it's from cameras and spectrographers and stuff. The only way to properly prove it would be to actually get a sample and put it in an analyzer. But something's going to have to change for that.
I suspect also that the rate of change is happening much quicker now, because when they did this in '67, obviously a man was going to go to the moon. Mm-hmm. So presumably that's why they did it. They did it in advancement of whether it was Russia or USSR as it was then, or America. They knew somebody they were trying, so they thought they'd preempt, get it all sorted, get the treaty sorted.
Yeah.
But things are changing much quicker now. The fact that there's a lot more privateering going on. Mm-hmm. They've got the CubeSats, which we've talked about before, so it's making it available to, the space exploration available to a lot people with a lot less financial ability. The autonomous robots that we've got now. The technology is so much more advanced than it was when we whacked the lunar rover on the Apollo missions. Mm-hmm. So perhaps this is the technology is now will overtake what was the treaties signed. So perhaps they are going to have to do that sooner rather than later.
Yeah, I mean, I don't know how. Obviously, this treaty was signed by governments. Does it apply to private enterprises?
Well, it's countries, isn't it? So I suppose whatever the base of that private enterprise, whatever base country that is in, they are
bound by that.
Bound by that.
Yeah. The other interesting thing about this as well is when I was reading into the treaty, it's on a website for the United Nations Office for Outer Space Affairs, which I didn't even realize exists.
There you go.
So they have a whole section on space law.
We'll probably have one of those, but it'll be one guy in a basement in Whitehall.
Yeah.
They'll have an entire building, but we'll have one guy.
Yeah.
In a shed. Which is the British way of doing things.
Yeah.
We do very good things as long as it comes out of sheds. Right. Well, I think we've probably finished that little topic now. So yes, it was good that they announced the water. It's bad that we can't do anything else about it. And we'll see what happens when somebody's at the stage where they're going to put another rover on, because there are a couple that are under development now as it stands, aren't they?
I'm not sure about rovers actually. I know there's a few more sort of satellite orbiter type missions going.
Right.
But yeah, I'm not sure about rovers.
I'm sure I've seen some labs with some new rovers being. Maybe that's just proof of concept.
Yeah.
Generally.
Yeah.
But yeah,
the ones that are there lasting so long.
Yeah, they're very surprised, aren't they? They've all outlasted pretty much what they were designed for. Mm-hmm. Anyway, so that's good. So we'll just keep an eye out and an ear out for what any progressions in that area. So that's now going on to my topic, which is it's a new material. Ooh. So we've talked about graphene before. Mm-hmm. Just to recall, to remind you all, it's a two-dimensional structure. It's a carbon-based two-dimensional structure. It's a one atom thick structure, so that essentially if you lay all like snooker balls out next to each other on a snooker table, that's the sort of effect that it would have. We've covered this before. We've said it's one atom high. We've said it's two-dimensional. We've said that it behaves like metal. It conducts electricity differently, and I'll come on to that with this new metal. And it's strong, and it's light, and it's stiff. So all good things, and they've got lots of applications where they're going to try and put the graphene to use. But this electrical conductivity is a bit. It's not consistent, and it's not. The way that the properties are, it doesn't lend itself to electrical conductivity very well. Heat conductivity, yes, but not electrical. So this brings me on to this new topic, this new subject, this new material. It's called phosphorine, and obviously they're doffing their cap to the graphene people. It's the actual official name is black phosphorus, and it's actually been around for like 100 years, but nobody did a damn thing with it until like last year.
Well, she's been sitting on a shelf somewhere.
It's been sitting on the shelf. They knew about it, and it was like, yes, check that. That's another one. That's another compound that we've got. So what they're doing is they're using last year they decided to pretty much like graphene. When graphene was invented, I think it was, if I recall rightly, it was a load of sort of students in a science lab that had very small, very thin layers of carbon, and that's how they managed to get this graphene. So with black phosphorus, they're working on very thin, 10 to 20 atom thick layers of this phosphorus, black phosphorus, and they're thinking this is going to be the new wonder material that beats graphene into a cocked hat. The reason why they think it's better than graphene is yes, it's thin. It has many of the structures, many of the things like graphene, but the biggest one that it has over graphene is its properties, semiconductor properties. If you look at this diagram, I'll just talk you through it. So this is the big thing about this phosphorine, or this black phosphorus, is that it has a band gap, a much bigger band gap that is tunable, which graphene doesn't have. Now this band gap, if I show you this diagram, this is basic semiconductor, basics of the semiconductor. You've got two bands. You've got a valence band and a conduction band, and this energy gap, this band gap here between the two, is a state of energy which no electron exists in this band gap. And the idea is that if you can get electrons to go pass from the valence band to the conduction band, you have conductivity. As the band gap increases, it becomes more and more of an insulator. Well, the problem with graphene is that it doesn't have it doesn't have like a band gap, so it's very hard to pass. You have to manually try and engineer this band gap to get this flow of electrons. But with black phosphorus, it's inherent. And the good thing about it is this energy gap, this band gap, can be fine-tuned for like over a fair old range. So I think it's about between 0.3 electron volts and 2 electron volts. So it's quite a wide spectrum. So far, so as soon as they got that flow of electrons, it can then be considered for semiconductor purposes, and in a way that it can surpass silicon. So far we've had it using this technology. There's a South Korean university which I won't attempt to pronounce, but
go on.
Oh, it's such my linguistic skills are just second to none. They really are. So it's the South Korean university. They've made a number of different transistors with using phosphorine, and it's comparable to the semiconductor properties of like silicon now, and it's got really big opportunity in optoelectronics as well.
So what's the advantage of it over silicon though? What's the
well, it's the thinness you can get,
right?
Because
yes.
it's this atom,
and the fact that it's tunable, so you can.
It's tunable, yeah. But it's the fact that you can get it down to sort of atoms, rather than because a substrate on an integrated circuit is still fairly thick. I mean, not to the naked eye, but it's still, in terms of atoms, it's still fairly thick. But this is what the thinking, that the optoelectronics properties of getting light connections, and they've already done some examples, and they've created a detector which converts light into electronics using phosphorine, and they've managed to get a sort of 3 gig per second light to electron flow. So it's good thing. This is what this is the good possible things. There are, however, some problems. And they're fairly big problems, actually.
Right. Okay.
But they have obviously managed to come to create it. So they're not insurmountable problems, but they're quite difficult. So the first one is it's man-made. So you create it by putting an existing phosphorus called red phosphorus under some pressure. And it's fairly big pressure. It's 1 gigapascal of pressure.
That's quite a lot of pressure.
That's a lot of pressure. But that's not it. That's not just the only thing. Whilst you're applying this gigapascal of pressure, you've got to heat it up to 1,000 degrees Celsius.
Okay, yeah.
And then once you have it in that state, the crystals that form can be peeled off. And they make these layers.
So
there's another.
Not going to be very quick to make this, is it?
Now they've got some things to overcome. It has to be said, but that's not the only thing either. There is another bad thing about. Under normal circumstances, when you expose it to air, it degrades within hours.
Right. Okay. So it'll only work in space. And you have to drop a city on it on the golden sun or something.
Yeah, so they reckon they can get around with the degradation of in air because they can apply some inert materials over the top of it to preserve it. But if they can get around all our manufacturing issues, it's a new super material.
Yeah, this always seems to be the problem with these. When you hear of like some new material or something, like you have I don't know the carbon nanotubes, and you hear about all the tensile strength, and it's amazing, and we can build something that we could stretch to the moon, and then it turns out, but we can only build like 1 millimeter a year or something, and it's like okay, none of them seem to be. I suppose I mean it's obviously it's cutting edge technology. It's not going to be an easy process, otherwise they would have been discovered and mass-produced years ago.
Yeah, I think that the fact that, I mean, like graphene, although they only really understood how making it very thin had all these properties, they've actually known about it for a long time. Yeah. It's when they were coming up with all of these original materials, and they were coming up with the periodic table initially in that time in the sort of like the Industrial Revolution and all that around that time. They knew about all these things, and I think they were like getting to the stage of like, oh, another one, we found another one, tick it off. Oh God, there's another one, and only now when the rate of finding these things has decreased, are they going back and thinking, well, let's now have a look at these. Yeah. Let's get some investigation done, and hence graphene came out like it was about 10 years ago, I think, that they really understood it. And this was only last year when they started doing genuine experiments into phosphorine. So,
see, graphene. There's a way of creating the single layer graphene that's really simple as well. I don't know if you've seen this. It actually does involve like a sort of a graphite. You get a graphite-based pencil or whatever. You draw on it, and then you get a bit of sticky tape. You just put it on the top and then peel it off. And a single layer comes off.
This is how they found it. It was they did this with it was a university in America, and it was a lecturer and some students, and they'd done some experiment with carbon, graphite, to be precise, and it had some sticky tape, and they'd found it in the bin. Yeah. And it's like, oh, it was they found this, but yeah, that was it. That was exactly how.
So that's like the other end of the manufacturing spectrum to this phosphorus. All you need,
too bloody easy that.
Although how you get it off the sticky tape, I don't know.
Because
another piece of sticky tape.
But it's interesting that we are now, and this is what I remember saying this at the time, that it was really interesting that we're in this time of new invention and new research, and it's opening the prospect of finding new things now again. There was a good few years where there was a bit of a lull, I felt. and graphene and this, phosphorine, and the space exploration with the CubeSats and all these things. There's a whole new thing. It's opening it up to more than the average, although obviously not phosphorine, because the average person does not have 1,000 degrees, able to produce 1,000 degrees Celsius and a gigapascal of pressure. But
it's interesting. So, if these phosphorine semiconductors, will this help us get over the sort of, in terms of semiconductor silicon based, we're reaching these levels now where we're
the micron
sort of
levels,
seven micrometers on that.
Yeah.
And they're starting. I know they're starting now to do 3D transistors. So rather than just being a single layer, it's now sort of layers on top of each other.
Yeah, multi-layered.
Get around this limit that we all, quite often you get these limits and then it turns out it's not a limit. But could this be the next thing that passes that limit?
Yeah, I mean this is what they're hoping for. This is because they've got they can move the energy band around, and it really does work like a semiconductor. Whereas graphene, they say that it was they call it a semi-metal, or
semi-metal.
Yeah, it's like a semiconductor metal,
right.
But it's not. It has some real problems in terms of electrical conductivity. And even though I was reading something just before I came on, there's some universities who have managed to fabricate this band. It's fixed. It's fairly small and it's fixed, so it has limited uses in terms of so computing. This is what they're going for. They're looking for anything that we can have, speed of light, communication, and that's what all of these things will be based on trying to find out this new method of doing speed of light communication. But so that's an interesting one, just because again, this I didn't I've only found it in one place, and that was the Institute of Electrical and Electronic Engineers in America. It was on their periodical. I've not seen it anywhere else.
Yeah. So
and we're obviously very, very at the start of it, whereas graphene's at least had about 10 years worth of work on it. But I still don't know. I still haven't seen any real
practical
genuine
uses.
Products made like graphene based stuff. So it's obviously going to take a few years. So anyway, that's my topic over, and it's. And we're kind of at the end. Really.
Now it's Richard's turn. Where is he?
Where is he? Damn him!
Perfect time.
So, you've got anything else to randomly discuss? Because we normally can, if we have a topic.
Did you see there was something in the news about America have finally run out of IPv4 addresses?
I did.
Yeah,
I did see that. Yeah. So
I know there was something a couple of weeks before about BT have announced what they're doing with their IPv6 transfer or whatever. But obviously it is definitely getting to the point now where that's really going to have to start kicking in. If they've officially run out of them in America, I don't know
the only places who have got IPv4 addresses are Africa now.
Right, okay. Did they just have an allocation that was never used because
of their infrastructure, I think.
Yeah.
But
will they be worth more money? Will there be like sort of certain industries or sectors that it'll cost them so much to upgrade to IPv6 that they want to buy more IPv4?
Well, you can't really do that. First off, IONA is the governing body, so they're the worldwide body for allocating IP addresses, and then they give them to the regional bodies. Like in Europe, it's RIPE. In America, it's ARIN. I think it's ANIC in Africa. I'm trying to think of what the African naming. Let me just have a look. Just talk amongst yourself.
Don't let ANIC control anything, blame me.
Just to be factually accurate, it's Afrinic.
Afrinic, okay.
Afrinic. Yeah, why didn't I think of that? Yeah. How could I not have thought of that? So IONA is a top level body. They allocate blocks of addresses, thousands and thousands of addresses to each of the different registries based on how much they think they'll be using. Obviously, if you're in Europe, America, and Asia, you'll have more IP addresses than if you're in Africa or the Pacific or something like that. So that's the first thing. They've all allocated them all. The individual registrars now have to manage them in their areas. If Africa, what you're postulating is like if Europe want to buy some from Africa, could you do possible? That? Yeah. Well, you'd have to. They'd have to keep all of the routing tables across the globe with these blocks that they're given to somebody else, and that would quite frankly be a nightmare.
Right.
Because it's already been allocated, and all of the routing tables have already been set. So Africa, you're having these. Europe, you're having these. So for somebody to say, I tell you what, we're going to give these Class Cs to Europe. You would have to maintain this gap in the routing table forever. Yeah. And I think that would be a bit of a management.
I mean, have you done anything with IPv6?
Yeah, I did it. I did it when I was at the company that shall not be named, the old company when you were there.
Right.
I did do some basic stuff then with the Linux.
Because I've looked at it and I've thought, this is going to be a nightmare to shout across the office. You know, the IPv4 ones are easy. You can just shout them across and it's this. But these
why are you using
like,
IPs and not DNS?
Well, if you want someone to set their DNS to an IP address, you tell them, that's what I mean. But it's because it's pairs of letters and numbers, isn't it?
Yeah. It's
like 16 of them or something. I can't.
Yeah, colon separated.
Yeah,
rather than dotted quads. It's. I think there's lots of people, and lots of fairly intelligent network professionals who are keeping. The reason why they're ignoring it and putting their head in the sand is because they don't want to deal with it. Quite frankly.
Yeah, I can imagine.
We understand it. I understand it.
Yeah.
But I remember when we were setting up our new network at the place where I used to work, the International Telecommunications Company with 2 letters. We actually disabled IPv6 in all of the new builds of all the software OSs.
Yeah.
So it's interesting, and I suspect a lot of people would be like that. But I think you can. You will be able to keep internal IP addresses as V4. I think I'm right in saying you can keep your IPv4 addresses internally and the have the IPv6 on the external. Gateways.
Yeah. So you won't have to change what our home address is from 127.0.
No, you'll still have your 192s or your 172s or your 10 dot whatever.
Yeah.
So this is really interesting times, and then of course Africa, they think they're going to run out in 2017.
Well, that's the thing. Since they put that what was that big underground cable that went in? It was only a few years ago, wasn't it? Their sort of infrastructure has massively just blown up, hasn't it? Now they've got
but then it snapped, didn't it? So for a while they had to go back to satellite internet, and then somebody stumped up some cash and got it fixed. So
it got hit by an anchor, didn't it?
Yeah, they'll need more than one cable.
To
have a diverse connection into a continent. You need more than one cable. To be honest, the easiest thing for Africa would be to run a cable from Tangier underneath straight to Gibraltar, because that is the closest place in Europe. Unless you want to, suppose you could come through Turkey and route it that way. But if you want to just connect from Europe to Africa, from Gibraltar to Tangier, that would be the because you can actually stand in Gibraltar and see Africa.
Right.
So it's not that far away.
Yeah.
So that would have been the best place to do it. I would have thought. But then there'll probably be loads of red tape and the millions of reasons why they couldn't do that. Because that would just be logical.
Yeah, that would be too easy.
Yeah. But interesting, yes. So Yeah, IPv4 is rapidly running out. IPv6 is everybody is going to have to be coping with that. And quite frankly, even though I'm saying that you can still have IPv4 internally, I'm going to put my head out and think that there was going to be a phase where if the network professionals are going to use IPv6 externally, they'll just use it internally as well.
Yeah.
In which case we'll all have to get used to the dotted the multiple colons separated notation, which will be lovely.
Yeah.
Yeah. Right.
I can't think of anything else.
No.
I think that was...
Well, we'll wrap it up. Actually, I was just going to say, because we're on episode 44 now, and being that we do one a week, and there's 52 weeks in the year, that means episode.
That's a good point. I never thought we were going to come to episode 52 at some point, aren't we?
So 52 was going to be our birthday.
Yeah.
So we're
we can have a party.
Yeah, we'll get streamers and everything. And but I if anybody wants some to come on the air and have somebody to talk about, that would probably be a good birthday celebration. If you want to do that, drop us details. As always, if you want to comment on what we've been saying this week or any week, and if you think we're wrong, right, or indifferent about the whole thing, you can use our Twitter handles. That's mine. Say hello, Ross.
Hello, there's mine. Yeah.
There you go. And then, of course, we've got other methods of internet communication. We've got email at oldfaithful wonderofstuff@gmail.com. We've got wonderofstuff.blogspot.com, and I think perhaps on our birthday would be a good time, if I can't get a way of hosting the blogspot.com address and the palindrome, that's mine, the wonderofstuff.com address, that would be a good time to switch over.
Yeah.
Maybe mark the first year and go with a wonderofstuff.com. Anyway, so that's all of the methods, all of the ways that you can get in touch with us. So until next time, when I'm sure Richard will be back and we'll have a full compendium.
Compendium?
No, we'll have everybody back.
That'll be the one,
yeah. We'll say goodbye.
Bye-bye.
Bye-bye now.